My name is Erika Lettrichová, and I'm a student at the Faculty of Mathematics, Physics and Informatics and Comenius in University. And in the following presentation, I will introduce our research of modeling specific fertility rates. We will start with what the specific fertility rate is. It is a relative analytical demographic indicator that indicates the number of live births to women at a certain age relative to the average number of women at the same age. How did the specific fertility rate curve evolve in selected countries? What trend do we anticipate for near future? Can we find a quality model that accurately describes the past trends? These are the questions we aim to answer during our research. In the graph, we can observe the development of the specific fertility rate in selected countries, including Slovakia, Czech Republic, Hungary, Austria, and the Netherlands, in the years 1970 and 2015. We can see that in 1970, the curve reached its peak for women aged 22 to 23 years, meaning that the women in this age group gave birth to the most children, and in 2015 the peak occurred for women aged 29 to 32 years. Delaying motherhood to a later age also affects the birth of second and subsequent children, and leading to a decline in the specific fertility rate. The goal of our work was to find the most suitable stochastic model for the studied population. In our research, we started from a Lee's model, which was published in 1993 in the article Modeling and Forecasting the Time Series of US Fertility by Ronald Lee. Let fxt represent the specific fertility rate at age x and calendar year t, and then following equation defines the model of specific fertility rate. Ax and bx are unknown age-specific parameters of the model that characterize the fertility rate at age x, and ft are unknown time-specific parameters of the model that characterize the effect of the calendar year on the fertility rate in year t. And last one, ext, represent the error that determines the size of the influence that the model failed to capture. The graphs provide a graphical representation of the estimated vector parameters ax, bx, and ft for the Slovak population within the age range of 15 to 44 years and the time range from 1960 to 2019. Lee's model in this case involves 120 parameters, and in case of a Lee's model, these estimated vector parameters can be nicely interpreted. Let's see at the parameter ax. It can capture the basic natural fertility levels, which are relatively low at the younger age, and then gradually increase, peaking around 22 to 23 years, and then decline with increasing age. And the beginning of the graph bx of the parameter bx is similar to ax, but the graph for bx only decreased between the ages approximately 23 to 28 years, which can be interpreted as capturing the difference between young mothers and older mothers. And then it rises again, which may indicate the effect of delaying pregnancy to older ages or higher order births. The most interesting graph is the last one, which shows development of the time factor ft between the years 1960 and 2019. It serves as something of a litmus test for birth rates in Slovakia, and the analysis of the time factor ft between these years reveals interesting trends in fertility rates in Slovakia. Let's start between years 1960 and 1970. There was a slight decline, infertility rates from initial high levels that were characteristic for post-war period. There was an increase in and stagnation in time factor between 1970 and 1980, often referred to as the era of Husak's children, which could reflect a generation of people influenced by the politicist of Gustav Husak. Subsequent, Next, there was a gradual decline in the FT coefficient between 1980 and 1990. Then there was a steep decline in fertility rates around 1991 to 2003. This one. This decline was attributed to various factors, including the shift to a market economy, increased demands in the workplace, or a rise in the number of university and college students, or delaying the first pregnancy and lower social safety nets and predictability in the capitalist system. Finally, there was an increase in the time-specific factor in later years. This was due to women who delayed their first pregnancies in 1990s, ultimately giving birth in early 20s, but at an older age, typically between 30 and 35 years. Additionally, there was a delayed birth phenomenon for the children of the Husak's generation, who also tends to have children at a later age, typically in their parents' higher age group. In our research, this model is referred to M1A model. However, this model cannot capture certain pieces of information, which remains in the residual term. In this model, the residual term should ideally consist only of random white noise. Therefore, we attempt to improve it by gradually adding time, age, and cohort parameters to obtain a model that provides the most accurate description of specific fertility rates. We tried 8 different model variants, and among them, models labeled as M6B and M7B appeared to be the most suitable. In the case of this model, the estimated parameters may not have a straightforward interpretation, as the model are highly parametrized, and the effects of parameters become more distributed among each other. However, our research demonstrated the need for using such complex model to better capture the complexity of fertility rate patterns. This model more complex model, while challenging to interpret directly, can provide more accurate and detailed insight into the factors influencing specific fertility rates, allowing for a more comprehensive understanding of the phenomenon under investigation. In a significant part of our work, we focused on estimating parameters of the introduced models. So let X in he, where he represents the set of observed ages of women, and T in tau, where tau is the set of observed calendar years. Then we define matrix FP as the average size of the X-year-old female population in year T, and LB matrix as the average number of live births to X-year-old women during the calendar year T. We assume that LB follows a Poisson probability distribution, and the set of parameters estimated for each model is denoted by symbol phi, and the specific fertility rate fxt can be formally represented as fxt phi, as each model depends on these parameters. Under the assumption of Poisson distribution, the logarithm of a likelihood function takes the following form. And the estimation of parameters was carried out by maximizing the logarithm of the likelihood function, and the anti-parameter estimation was processed by using the software R, employing the optim function. For the M1A model, the likelihood function was optimized using the Broyden-Fletcher-Goldfarb-Shannon algorithm, which belongs to quasi-Newton methods. For the estimated models M2A to M8B was used two-step optimization process. In the first step, the Nelder-Mead algorithm was used, which is a robust method. It falls under the class of simplex method. In the second step, the VFGS algorithms was applied, known for being faster and more precise than Nelder-Mead algorithms. The two steps approach was chosen due to a large number of estimated parameters, where the Nelder-Mead algorithm tends to achieve better convergence to a semi-optimal point. The parameters obtained in first optimization step were then utilized as a starting parameters for the BFGS algorithm, increasing the likelihood of the algorithm converging to optimal point with the chosen numerical precision. This approach helps improve the efficiency and accuracy of parameter estimation, especially in cases involving complex model with a higher number of parameters. To assess the suitability of the models, we compared them based on the value of the logarithm of the likelihood function and through the Bayesian information criterion, often denoted as bits. The bits criterion takes into account not only the likelihood function, but also the number of estimated parameters, providing a penalty for models with a higher number of parameters. We consider the following modified version of bits, where L-phi represents the maximum value of the logarithm of likelihood function, and is the number of observation, and Ni is the number of estimated parameter in the model. This modified definition of bits helps in model selection by penalizing models with more parameters, aiming to strike a balance between more complexity and goodness of fit to the data. A lower bits value generally indicate the better trade-off between model fit and complexity, making a corresponding model better for the given dataset. To verify quality of a used model, we estimated the residuals of these models, and the process involved dividing the time intervals into data windows, which were shifted by 1 year in subsequent calculation. The first step in each data window was the estimation of model parameters. Based on data from this data window, we estimated the model parameters using the method of maximizing the logarithm of likelihood function. The obtained parameter estimates were then used to calculate model-specific fertility rate by using both the model-specific fertility rate and the fertility rates obtained from the human fertility database. We computed the residuals of the model using the following formula, and this process yielded a matrix of estimated residuals that we further work with. We approach the assumption that the number of live births follows a Poisson distribution, and with a sufficiently large number of births after appropriate transformation and normalization, it converges to a normal distribution. We consider the normality of the model as an added characteristic and tested the presence of normal distribution in the matrix of estimated residuals. And if the additional hypothesis of normality of the model is not rejected, it allows us for the use of procedure, tests, and techniques in further mathematical modeling and fertility rate and prediction that require this assumption of normality. To test for the normality of estimated residuals, we used normality test. Specifically, we employed the Jacques-Berat test and its a modified version, the Shapiro-Wilk test, and the Kolmogorov-Smirnov test. For the testing independence of residuals, we used heat maps, which display the values of metrics of estimated residuals. We expected that the heat map exhibit a random pattern similar to white noise. No cluster or regular pattern should be visible. And if clusters or regular patterns are evident on the heat map, the hypothesis of independence should be rejected. We decided to examine the suitability of models for stochastic modeling of specific fertility rates in the Slovak, Czech, Hungarian, Austrian, and Dutch population. We were interested in determining which of the models used would be the most suitable for each population. The population we selected have similar trends in fertility development, and therefore we did not expect significant differences in the suitability of the models used. To compare the quality of the models, we choose a consider age, time range, and consistent age and time range for the data. The specific fertility rate is typically calculated within a woman's reproductive age, which falls within the range of 15 to 49 years. Since the number of children per woman decreases as age increases, we chose an upper limit of 42 years for reliability. Similarly, for a woman age 15 to 17, there is a low number of births, which could increase the error in our model. Therefore, we decided to set the lower age limit at 18 years. The chosen time period was based on data in the human fertility database. So we selected the years 1960 to 2019. Now let's move on the result for obtained for the Slovak population. In figure, we can see the trend in specific fertility rate in Slovakia. We observe a decline in a specific fertility rate over the years of observation, but we can also notice a shift in the age with which the specific fertility rate is highest, moving from age 23 to age 30. To describe this development, we seek to find the most suitable model. Here you can see the results of the quantitative comparison of the models for Slovak population. The table displays the median value of logarithm of the likelihood function, which represent the median of all the likelihood values obtained during the parameter optimization. In the observed years, model M7B achieved the highest median value of the logarithm of the likelihood function. However, this model involved estimating 179 parameters, which had a negative impact on the bits value. So based on the bits criteria, the model M6B was identified as the most suitable model due to its lower complexity. On this side, we can see the result of the qualitative assessment of model suitability, specifically the result of normality test of the residual from the p-values of the normality test for the estimated residuals of model M6B. We can see that all values are above commonly used levels of significance. Therefore, we do not reject the hypothesis of normality for these residuals. To assess the independence of residuals, we used visual assessment based on the use of heat maps. Here we can see the heat map of model M1A, where we observed significant cluster and diagonals, which can be interpreted. So we can see here a dark spot. So this can be interpreted as a sharp change in the fertility process that these models fail to capture. And next, the white area can be also described as another sharp change in the fertility process that the Lee's model was unable to capture. In this area, we see high positive errors indicated an increase in fertility rates compared to the period around the turn of millennium. So for the comparison, we can see the heat maps of model N1A and model N6B, the model that emerged as the most suitable for the Slovak population. In the case of Slovak population, Lee's model has a much higher level of absolute error compared to model M6B. here we can see that there is a range between -15 and 15, and here we can see that the level is between -3 and 4. So based on this comparison, we can conclude that model M6B is more suitable for Slovak population. So in our quest to find the most suitable stochastic model for the specific fertility rate, we started with the basic Lee model. The parameters of this model have a clear interpretation. However, higher order models, which we obtain by adding various combination of time, age, and cohort parameters, do not have such a straightforward interpretation, as their effects become more distributed. Nevertheless, our research demonstrated that despite the very high number of parameters in these models and the loss of interpretability, it is necessary to use this model complex construct. The problem with the basic Lee model was that its 3 parameters couldn't capture certain pieces of information hidden in the data. Some information remained in the residual term, which in this type of model should ideally have the characteristic of random white noise. So, however, our study showed that this was not the case with Lee's model, and the residual term contained a lot of information. That's why it became evident that expanding Lee's model with the additional parameter vector are capable of capturing this information was necessary, and such an expanded model can be used, for example, in predicting future specific fertility rates. So thanks for your attention.
Okay, thank you a lot, Erika. Clap, clap. So are there any questions? Shikica, please, and Martina.
Okay, well, actually, I have a question which is rather historical. So when you look into the data from the 60s up to the Velvet Revolution, you have the data for Czechoslovakia as a country. And my question is Slovakia comparable to Czechia at this point? And also when you chose the other countries, which are Hungary, the Netherlands, and etc., my question is, was the economic development anyhow correlated with the birth rates? For example, in our country of Yugoslavia, we had quite different situation in the Federal Republic of Slovenia, for example, and in the province of Kosovo. So, so this is a question because when you analyze the historic data, is it comparable between Slovakia and Czechia? Thank you very much. It was a nice talk.
Okay, thank you for your question. So our model do not include or we can't say that the process of how to say some economic changes like directly sorry the economic changes directly affect the fertility rate. So it's not the parameter in our model. It's a different type of model. But we can see that in Slovak and in Czech Republic, in Slovak the decline is much higher than in Czech Republic. So we can say that the Czech Republic is better in the fertility rate, but we can say that our models are capable of catching this information directly.
Great. We also have a question for Martina. Please.
Yeah. Hi, thank you for the nice thought. I had a similar question actually, but I have another one, which is whether you like in your data you had only the birth of the first kid or any child.
We have any child. We do not specifically look at the first order fertility rate, but any child.
Yeah, and another like maybe more philosophical question, but there was a period, I think in the 80s and 90s, where the elementary school had 8 years, not 9 years. And then they like changed it back to 9 years. And I was wondering whether this could have like any influence on the fertility rates, because your life kind of evolves around school. So it sort of like switches when you end school by a year. So I was wondering whether this could somehow be included in the model or whether that is just too complicated.
It's like I think it's like the same question as the economic parameters. So we can just look back and have a like assumption that it can be, but we can like say it 100% it's because of this.